Picture the oldest thing you have ever held. A grandmother's ring, perhaps. A coin worn smooth by a dozen centuries of human hands. A fossil pressed into limestone 300 million years before the first tree grew. Now picture something older. Something so much older that the numbers lose their grip on language, and you have to reach for metaphor just to carry the thought across a room. Picture the universe itself. The whole of it. Every galaxy and void, every photon and gravitational wave, every atom that was ever forged inside a dying star, and ask yourself, how old is it? For most of your life, if you asked that question in a school, a library, a television studio, or a research institution, you would have received the same answer: 13.8 billion years. That number was not a guess. It was the product of the most precise measurements in the history of science, derived from multiple independent methods, cross-checked by satellite data stitched across decades, and enshrined in textbooks on every continent. It felt settled, final, carved. Then a gold-plated mirror 18 times the width of a dinner table swung open in the cold of deep space and began to look back. And what it found has forced the most consequential rethink in modern cosmology. What does it mean when the most powerful telescope ever built finds galaxies that should not exist? What does it mean when the universe's own expansion cannot agree on a single value? When two equally rigorous sets of scientists, measuring the same cosmos with the same physics, arrive at answers that differ by more than 8% and refuse to converge? What does it mean if the age of the universe, the single number from which almost everything in our cosmic history is derived, is simply wrong? These are not fringe questions. They are the questions now sitting at the centre of professional cosmology, debated at CERN, published in Nature, and whispered between Nobel laureates in conference hallways. The James Webb Space Telescope did not quietly confirm what we already thought. It sent a set of observations back across 13 billion light-years and landed them, one after another, in the lap of a standard model that is now struggling to absorb the shock. This is that story. To understand why the number 13, 8 billion matters so deeply, why a potential revision to it is genuinely unsettling to the people who have built their careers around it, you have to understand what that number actually is and what it actually does. Because it is not merely an age the way a person has an age. It is a load-bearing wall in the architecture of everything we know about the cosmos. Pull at it, and the whole building has to be redrawn. The story of how we arrived at 13.8 billion years is one of the great detective narratives in science. It spans more than a century and runs through some of the most dramatic intellectual reversals ever staged in a physics department. It begins, as so many cosmological stories do, with a question that sounds deceptively simple. Is the universe the same size it always was? For most of human history, the answer seemed obviously yes. The heavens were fixed, eternal, and unchanging. The stars were points of light sewn into the fabric of an infinite and permanent sky. Then, in the 1910s and 1920s, a Slovenian-born astronomer named Vesto Sliffer began systematically measuring the spectra of spiral nebulae, those fuzzy patches of light that no one had conclusively identified, and found something peculiar. Their light was shifted, redshifted. That is, the wavelengths of light arriving from these objects were stretched out toward the red end of the spectrum in a way that suggested they were moving away from us. Not just one or two of them, almost all of them. A stretched wavelength of light is the cosmic equivalent of a sound that drops in pitch as the source moves away. The Doppler effect applied not to sound waves in air, but to electromagnetic radiation crossing the void. When Sliffer tallied his measurements in 1917, 36 of the 41 spiral nebulae he had measured were receding. That fact sat in the literature, for a decade before a young astronomer named Edwin Hubble pointed the 100-inch Hooker telescope at Mount Wilson in California toward those same objects and confirmed, in 1923, that they were not nebulae inside our galaxy at all. They were galaxies in their own right, island universes, each containing billions of stars, scattered across distances that beggared the imagination, and they were fleeing. By 1929, Hubble had assembled enough measurements to publish the relationship that still bears his name. The further a galaxy is from us, the faster it recedes. The universe is expanding. Not merely growing, but expanding in the specific way that suggests everything was once in the same place, that if you ran the cosmic film backward, all of it would converge on a single point at a single moment we now call the Big Bang. That relationship, the Hubble constant, designated h0, is the key to the age of the universe. If you know how fast the universe is expanding, you can calculate roughly how long it has been expanding. The reciprocal of the Hubble constant gives you a timescale. Run it in reverse with the correct physics, account for the way gravity and dark energy have tugged on that expansion across the eons, and you arrive at an age, at 67, 4 kilometers per second per megaparsec, the value derived from the most precise measurements of the early universe. From the European Space Agency's Planck satellite in 2018, the age of the universe works out to approximately 13.8 billion years. But note the phrase I just used, the most precise measurements of the early universe, because there is another way to measure the Hubble constant. You can measure it from the late universe, from nearby galaxies, from pulsating stars called Cepheid variables, from exploding stars called Type Ia supernovae. And when you do that, you get a different answer, not by a little. By enough to matter catastrophically, the Planck value of h0 is 67.4 km per second per megaparsec, with an uncertainty of plus 0.5. The value derived from the Esachia's team, supernovae h0 for the equation of state, measuring Cepheid variables and Type Ia supernovae in the late universe, is 73.04 km per second per megaparsec, with an uncertainty of plus minus 1.04. That difference of roughly 8% may sound modest, but it carries a statistical weight that has physicists treating it like a fire alarm. The two measurements are in disagreement at more than 5 sigma, a threshold that, in particle physics, is the formal definition of a discovery. In cosmology, it means one of two things. Either one or both measurements contain a systematic error no one has yet found, or the standard model of cosmology is incomplete in a way that no one yet understands. This is the Hubble tension, and it is the context into which the James Webb Space Telescope was born, funded at the extraordinary cost of $10 billion and launched, after 3 decades of development, 2 near cancellations, and cost overruns that made congressional committees openly contemptuous, on Christmas Day 2021, inside an Ariane 5 rocket lifting off from Kourou, French Guiana, carrying with it the hopes and anxieties of an entire generation of astronomers. I think it is worth pausing to register what that launch actually represented. The James Webb Space Telescope had taken 30 years to build. There were scientists who had devoted the entirety of their careers to its construction, who did not live to see its first image. There were others who had fought for its survival through budget crises that nearly ended it, who stood in monitoring rooms on Christmas morning with their hearts in their throats. The telescope was so complex, so precisely aligned, so exquisitely calibrated for temperatures just a few degrees above absolute zero, minus 233 Celsius, that a single deployment failure in any of its 344 single-point failure components would have been catastrophic and irreversible. No repair missions, no second chances. One shot at perfect deployment 1.5 million kilometers from Earth. It worked. Everything worked. All 344 mechanisms deployed correctly. The 6 5-meter primary mirror, composed of 18 hexagonal gold-coated beryllium segments, each machined to an accuracy of a few tens of nanometers, opened like a slow brass flower in the dark, unfolded precisely as designed, cooled to its operating temperature, and began to receive photons that had been travelling toward it for the age of the solar system. The first images, released on the 12th of July 2022, reduced grown scientists to tears, the cosmic cliffs of the Carina Nebula, a quintet of galaxies in gravitational embrace, the atmosphere of a distant exoplanet analysed in a single exposure, and the first deep field, a patch of sky the size of a grain of sand held at arm's length, packed with thousands of galaxies, some of them seen as they existed less than 1 billion years after the Big Bang. The world gasped at the beauty of those images, but working astronomers saw something else. They saw the tool that might finally break, or finally explain, the Hubble tension. And then, within months of science operations beginning, the data started arriving, and some of it was not what anyone expected at all. Every field of science has a moment where a single observation rewrites the syllabus. In particle physics, it was the detection of the W and Z bosons. In biology, it was the Mendelssohn-style experiment confirming DNA replication. In observational cosmology in the early 2020s, that moment came quietly, through a data file labelled GLASS Z13, and then came again and again and again, until the field had accumulated enough anomalies to demand a reckoning. Let us start at the beginning of the deep cosmic timeline, because to appreciate why James Webb's early galaxies are so deeply disruptive, you have to understand what the standard model of cosmic evolution actually predicts. In the lambda CDM model, lambda for the cosmological constant representing dark energy, CDM for cold dark matter, the universe after the Big Bang goes through a sequence of phases with a logic as predictable as the growth of a tree. In the first 3 minutes, the extreme temperatures forge the light elements: hydrogen, helium, traces of lithium and deuterium. For the next 380,000 years, the universe is an opaque plasma, a dense fog of electrons and photons so tightly coupled that light cannot travel freely. Then, as the universe cools to approximately 3000 Kelvin, electrons and protons combine to form neutral hydrogen atoms, a process called recombination, and the fog clears. Photons stream freely for the first time. We see those photons today as the cosmic microwave background, the oldest light in the universe, now cooled by cosmic expansion to just 2.725 Kelvin above absolute zero. After recombination, there follows a period cosmologists call the Dark Ages. The universe is filled with neutral hydrogen gas and dark matter, but there are no stars yet, no sources of light, no radiation. Just gravity, slowly working on the very slight density fluctuations seeded into the early universe, drawing matter together into filaments and clumps that will eventually become the first galaxies. This process takes time, meaningful time. In lambda CDM, the first stars are not expected to ignite until perhaps 100 to 200 million years after the Big Bang, and the first recognizable galaxies, small, irregular, rapidly star-forming, built from a population of population 3 stars, burning with a ferocity we have never directly observed, should not accumulate significant stellar mass for several hundred million years more. By roughly 500 million years after the Big Bang, according to the Standard Model's predictions, the universe should contain young, relatively small, still-forming galaxies, stellar masses in the range of a few hundred million solar masses. Nothing too polished, nothing too massive, nothing that looks like it has been at the business of star formation for a very long time. The Milky Way, with its roughly 250 billion solar masses of stars, took billions of years to assemble. The Standard Model is explicit about this. Structure grows hierarchically. Small things form first. Large things are built from mergers of smaller things over enormous spans of time. This is the prediction. Now let me tell you what the James Webb Space Telescope found. Within weeks of the first science data being released in 2022, a team led by astronomer Ivo Labbé of Swinburne University of Technology published a paper in Nature that sent a tremor through the field. Using JWST's near-infrared camera, the NIRCam Labbé and colleagues had identified 6 candidate galaxies, not confirmed by spectroscopy at that point, but identified by their photometric redshifts, that appeared to exist between 500 and 700 million years after the Big Bang, in the very early universe where lambda CDM expected only modest juvenile structures. The masses inferred for these galaxies were extraordinary. Some appeared to contain stellar masses of up to 100 billion solar masses. One candidate suggested a stellar mass potentially reaching 1 trillion solar masses. These were not small, irregular, freshly assembled structures. These were massive, mature systems, some of them apparently as large or larger than the present-day Milky Way. Somehow assembled in a cosmic environment that should have had nowhere near enough time to build them. I will be honest with you, when I first encountered these numbers, I had to go back and read them twice. 100 billion solar masses, 500 million years after the Big Bang. That is not a footnote. That is a structural challenge to the entire chronology of cosmic assembly. If these objects are real, and real at the masses initially estimated, then either the early universe was forming stars at rates that exceeded what our models consider physically possible, or the cosmological timeline itself was longer than 13.8 billion years provides for. The scientific community's initial response was measured. Photometric redshifts, it was correctly pointed out, are not spectroscopic redshifts. A photometric redshift is derived from the shape of a galaxy's light profile across multiple colour filters. It is an inference, not a measurement. The error bars can be substantial. Some of the most extreme candidates, it was suggested, might turn out to be galaxies at much lower redshifts that happen to mimic the photometric signature of very distant, very massive objects. Contamination by active galactic nuclei, the blazing accretion disks around supermassive black holes, could inflate the apparent stellar masses. Dust, always the cosmologist's nemesis, could redden and reshape spectra in ways that fool even sophisticated algorithms. These were valid objections, and they were exactly the kind of objections that spectroscopic follow-up observations were designed to address. Over the following year and a half, as JWST's near-infrared spectrograph, NIRSpec, accumulated data, the photometric candidates began to yield to definitive spectroscopic confirmation. Some were indeed lower redshift interlopers. Their initial photometric redshifts were revised downward. The field breathed somewhat easier, but not all of them were false alarms. In May 2024, a team led by Stefano Carniani of the Scuola Normale Superiore in Pisa published in Nature the spectroscopic confirmation of two luminous galaxies at a redshift of 14. One of them, JWST 14-0, was confirmed at a redshift of 1432. Let us unpack what that number means. A redshift of 1432 means that the universe was 3.32 times smaller in every dimension when the light from this galaxy was emitted than it is today. The light has been travelling toward us for approximately 13.5 billion years. When this galaxy was shining, the universe was perhaps 280 to 300 million years old, and yet it was already large enough, luminous enough, and chemically enriched enough to be unambiguously identified as a galaxy, with an active stellar population and the spectroscopic signatures of oxygen, an element that can only be produced inside stars and distributed by supernova explosions, meaning that at least one full generation of stars had already been born, lived, and died before the universe was 300 million years old, 150 parsecs across, producing stars at a rate of roughly 20 solar masses per year. That is a rapid and industrious stellar factory operating in the universe's first few hundred million years in a place and at a time where the standard model expected relative quiet. This object is not a photometric artifact. It is a real galaxy at a confirmed redshift, doing things that the model did not predict at that epoch. And then in 2025, JWST 14-0's record fell. A galaxy designated MOM Z14, first imaged by NIRCam on the 16th of May 2025, was spectroscopically confirmed by NIRSpec at a redshift of 14.4. The light left this galaxy when the universe was approximately 280 million years old. It is, as of this writing, the most distant galaxy spectroscopically confirmed in the history of astronomy, a galaxy existing at the very edge of cosmic dawn, when the universe had barely drawn its first breath by stellar standards. And yet there it is, bright, massive, real. But the most structurally damaging discovery from JWST's early deep field observations was not any single galaxy at a record-breaking redshift. It was a population of objects that should not exist in the numbers or at the masses in which they appear. In early 2024, a team reported observations of ZFUDS 7329, a galaxy observed as it existed 5 billion years ago, meaning a look-back time of 11.5 billion years, which had a stellar mass of approximately 100 billion solar masses and a stellar population estimated to be around 5 billion years old at the time of observation. Work backwards. If the stars in this galaxy were 1.5 billion years old, when the universe was 2.3 billion years old, those stars formed in the first 800 million years of cosmic time, and they then stopped forming, leaving behind a massive quiescent galaxy that had already run through its star formation budget before most of the modern universe's galaxies had really begun assembling. The analogy would be a human being who had completed their full adult development by their 4th birthday and then simply stopped growing. These objects are being called, in the evocative shorthand of research papers and conference talks, the red monsters. They are red because their old stellar populations and high dust content push their light toward the infrared. They are monsters because their masses exceed what the standard model says should be possible at their epoch by factors that no parameter tweak has yet fully absorbed. And here is what I find genuinely arresting about this situation. Not just scientifically but personally, these are not marginal detections. They are not statistical whispers in noisy data. They are bright, confirmed, spectroscopically measured objects sitting in the data in plain sight. And the field's honest response is that no one has a complete explanation for them. The standard model has been stretched in various directions to accommodate some of them. Early dark energy, enhanced star formation efficiencies, more active and luminous black holes contributing to apparent stellar masses. Each explanation has merit. Each explanation has limits. None of them fully dissolves the problem, and the problem keeps growing as JWST stares longer and deeper into the early universe, and keeps finding galaxies doing things they are not supposed to be doing yet. So what does this mean for the age? Does it simply mean the galaxies grew faster than expected, within a 13.8 billion year old universe? Or does it mean something more fundamental, that the universe itself is older than we think, that there was more time before those early galaxies for the raw material to accumulate? The answer, it turns out, depends entirely on which thread of the cosmological crisis you decide to pull first. In the natural sciences, a disagreement between two measurement methods is, in the first instance, treated as a measurement problem. One team made an error, or both teams made errors in different directions, and the truth lies somewhere in the middle. This is the default response because it is almost always correct. Instruments malfunction, calibrations drift. Assumptions embedded in data reduction pipelines contain hidden systematic biases that take years to identify. Science is full of apparent paradoxes that dissolved into calibration errors once someone looked closely enough. The Hubble tension has now been looked at closely enough to fill several thousand peer-reviewed papers and multiple dedicated international conferences, including the CERN workshop on tensions in cosmology, held in 2025, which opened with the explicit statement that the Hubble tension has reached the 5 sigma confidence threshold and is currently considered the biggest crisis for the lambda CDM standard model of cosmology. 5 sigma. That is not a rumour. That is a declaration. To understand why the tension is so stubborn and so unsettling, you have to understand the two measuring rods it puts in conflict. The first measuring rod is the cosmic microwave background. The CMB is the light released at recombination, 380,000 years after the Big Bang, when the universe first became transparent. It carries in its temperature fluctuations tiny variations at the level of 1 part in 100,000, a complete acoustic record of the early universe. The way sound waves propagated through the pre-recombination plasma imprinted a characteristic scale on the CMB, a pattern of hot and cold spots that peaks at a specific angular size on the sky. By measuring that angular size with extraordinary precision, and by knowing the physics of the early universe well enough to calculate what the physical scale of those sound waves should have been, you can derive the geometry of the universe, its total energy content, and, crucially, its current expansion rate. The Planck satellite, whose final cosmological parameter results were published in 2020, performed this measurement with an uncertainty of 0.5 km per second per megaparsec, its answer, H0 67.4 plus 0.5 kilometers SCOM PC. Age of the universe approximately 13.8 billion years. The second measuring rod is the cosmic distance ladder, a chain of overlapping distance measurement techniques that carries us from the immediate neighbourhood of the Milky Way out to cosmological distances by passing through a series of calibrations. At the nearest rung we use geometric parallax, direct triangulation of nearby stars, using Earth's annual orbit around the Sun as a baseline. At the next rung, Cepheid variable stars, whose absolute luminosity is tightly correlated with their pulsation period, through a relationship first discovered by Henrietta Swan Leavitt in 1908. You measure the period, you derive the luminosity, you compare it to the apparent brightness, and you have the distance, the same logic as knowing a candle's wattage and measuring how bright it appears. Cepheids carry you out to distances of roughly 40 megaparsecs. Beyond that, you calibrate Type Ia supernovae, a class of stellar explosion with a remarkably consistent peak luminosity, making them the most powerful standard candles in cosmological distance measurement, visible across billions of light years, using Cepheids to calibrate the supernovae and the supernovae to measure the expansion rate. The JWST team, led by Nobel laureate Adam Riess at Johns Hopkins University, has measured H0 73.04 plus 1.04 kilometers C. Higher, significantly higher, an 8% difference that carries a 6 sigma statistical weight. A higher Hubble constant means a faster expanding universe. A faster expanding universe has been expanding for less time to reach its current size. If H0 is 73 rather than 67.4, the age of the universe contracts from 13.8 billion years to something closer to 12.5 to 13 billion years. JWST's early galaxies suggest the universe needs more time, not less. These two conclusions point in opposite directions, and both of them are in tension with the standard model. This is the compound crisis, and it is why I think this moment in cosmology is genuinely extraordinary in a way that is difficult to convey without sounding hyperbolic. You have the Planck measurement of H0, indisputable in its internal precision, derived from the most detailed map of the CMB ever assembled, published by hundreds of scientists over a decade of data analysis, pointing one direction. You have the SUE's measurement, equally rigorous, built on a century of distance ladder methodology, confirmed by multiple independent research groups, pointing another direction. You have JWST findings, suggesting that neither direction is sufficient to explain what the early universe actually looks like. One attempted resolution came from an unexpected quarter. In early 2024, the Chicago Carnegie Hubble program, led by Wendy Friedman of the University of Chicago, one of the great names in extragalactic distance measurement, published JWST-based measurements of the Hubble constant, using not Cepheid variables but an alternative distance indicator. The tip of the red giant branch, or TRGB, and the J-region asymptotic giant branch, or JAGB method. Friedman's JWST results came in at 80.6 km/pp, a value tantalizingly positioned between the Planck result and the SH0ES result, suggesting that perhaps the Cepheid calibrations at the base of the SH0E's distance ladder carry systematic errors that inflate the inferred expansion rate. If Friedman is right, the tension might not be 5 sigma. It might be a gentler 2 to 3 sigma, the kind of discrepancy that historically resolves into calibration refinements rather than new physics, but it has not resolved yet. And as of 2025, the SH0S team has cross-checked its Cepheid measurements using JWST's superior resolving power. The telescope was designed in part to test whether Hubble Space Telescope Cepheid measurements suffered from crowding errors in dense stellar environments, and the result was that JWST confirmed the Cepheid distances. This H0 value held up. The tension remained Adam Riess, who shared the 2011 Nobel Prize in Physics for the discovery of the accelerating universe, itself the result that introduced the cosmological constant as a physical reality and gave lambda CDM its L, has spoken with characteristic directness about what this means. The two measurements are simply not compatible within lambda CDM. Something is missing from the model. Either there was a period of additional energy density in the early universe, what theorists have called early dark energy, that briefly accelerated expansion before the CMB snapshot was taken in a way that would shift the Planck-inferred H0 upward. Or there is new physics operating in the late universe that changes the expansion rate in ways not captured by the standard dark energy parameterization. Or, and this is the most radical possibility, the lambda CDM model itself is missing something more fundamental, something whose absence we are only now beginning to perceive clearly enough to name. And here is where the architecture of this crisis reveals its true scale, because it is not just the Hubble constant, it is not just the early galaxies. There is a third thread, one that is equally strange and even less explicable. Pulling at the same corner of the cosmological tapestry, it is the question of what the universe looks like at the very largest scales. What it looks like, apparently, is wrong. There is a principle at the foundation of modern cosmology that is so deeply embedded in the mathematics, so thoroughly assumed in the models, so rarely questioned in the professional literature, that it functions less like a hypothesis and more like a silent axiom. It is called the cosmological principle, and it states that the universe, when viewed at sufficiently large scales, is homogeneous and isotropic. Homogeneous means the same in every location. Isotropic means the same in every direction. Together they mean no special places, no special directions, no cosmic centres, no cosmic edges. The universe is, on the largest scales, a smooth and uniform medium with only small statistical fluctuations in density. This principle is not arbitrary. It is the simplest possible assumption consistent with the observed universe. It allows the Einstein field equations of general relativity to be solved for the universe as a whole, rather than requiring a full accounting of every gravitational source. Without it, modern cosmology as we know it is not computable. Without it, the CMB analysis that gives us 13.8 billion years does not work. Without it, the very concept of the expansion rate as a single number, rather than a patchwork of locally varying values, falls apart. The cosmological principle is testable. It predicts that the universe should become smooth, that structures should stop appearing above a certain scale. That scale has traditionally been estimated at around 300 to 400 megaparsecs, roughly a billion light years. Above that scale, the density of matter should flatten out into a near uniform distribution, like a fog that looks bumpy close up but becomes a seamless haze from a distance. Now consider a structure discovered in June 2021, not by a large international consortium, but by a PhD student. Her name is Alexia Lopez. She was a doctoral candidate at the University of Central Lancashire in Preston, England, studying the distribution of galaxies in a catalogue of quasar absorption systems spanning billions of light years. In the data, she found a curved arrangement of galaxies and quasars spanning approximately 3 billion light years, an arc stretching across roughly 1 gigaparsec of space, nearly symmetrically arranged, located approximately 9.2 billion light years from Earth. She called it the giant arc. The giant arc is not supposed to exist. A structure 3.3 billion light years across is by more than a factor of 3 larger than the theoretical upper limit on structures predicted by the cosmological principle. Probability of such a structure arising by chance in a universe where the cosmological principle holds is estimated at roughly 3 in 10,000. That is the kind of improbability that makes statisticians uncomfortable and cosmologists very quiet at dinner. Lopez published her result in 2021, and the scientific community's reaction was appropriately cautious. Single anomalous structures can arise in any sufficiently large dataset by chance. The universe is vast and rare things happen. One anomaly is a curiosity. Then, in January 2024, Lopez published again. The new structure she had found in the same region of sky was designated the Big Ring. It is a ring-shaped configuration of galaxies and quasars, nearly geometrically circular, with a diameter of approximately 3 billion light-years and a circumference of approximately 4.1 billion light-years. It spans 15 degrees across the sky. It sits at the same cosmic distance as the giant arc, approximately 2 billion light-years, and the two structures are only 12 degrees apart in the sky, suggesting they may be physically associated. The Big Ring is not supposed to exist either. A ring 1.3 billion light-years in diameter, almost perfectly circular, with no known physical mechanism in lambda CDM that would create such a shape at such a scale, appearing in the same region of space as a previously known anomalous structure of similarly impossible size. The probability of this being a chance alignment in a universe that obeys the cosmological principle is, by any reasonable statistical analysis, extremely small, and the giant arc and the Big Ring are not alone. There is the Hercules Corona Borealis Great Wall, a filamentary structure spanning approximately 10 billion light-years, discovered in 2013 and still debated, but not yet dissolved by subsequent analysis. There is the Sloan Great Wall, at 38 billion light-years, one of the largest known structures, predating JWST's observations entirely. There is the giant arc's predecessor, the Huge Large Quasar Group, a clustering of quasars spanning roughly 4 billion light-years discovered in 2012. Taken individually, each of these structures can be explained away as a statistical outlier or dismissed as a product of selection effects in the survey data. Taken together, they form a pattern that an increasing number of cosmologists are describing not as a collection of coincidences, but as a systematic signal. The universe, at the largest scales we can observe, may not be as smooth as the cosmological principle requires. And if it is not smooth, if the cosmological principle is only approximately true rather than rigorously true, then every calculation that rests upon it, including the calculation that gives us an age of 13.8 billion years, carries an error of unknown size. This is the depth of the challenge. It is not a single crack in the model. It is a set of simultaneous strains, the Hubble tension pulling one wall, the early massive galaxies pulling another, the large-scale structures straining the floor. And the question the field is now genuinely wrestling with is whether these strains share a common cause, whether there is a single missing ingredient whose inclusion would relax all of them simultaneously, or whether each represents an independent deficiency in our understanding, demanding separate and distinct new physics to address. I find this situation, the situation where multiple independent anomalies are converging simultaneously, more intellectually honest than any single dramatic announcement. This is what a genuine paradigm under pressure actually looks like. Not one experiment that disproves everything. A slow accumulation of data points that refuse to line up with what the model predicts, each one explicable in isolation, collectively forming a portrait of incompleteness. And now I want to tell you about the scientist who stepped into this accumulating crisis with a proposal that electrified some researchers, infuriated others, and crystallized a question that the field had been trying not to ask too loudly. What if the universe is simply twice as old as we think? Rajendra Gupta is a professor emeritus at the University of Ottawa. He is not a renegade outsider. He is a published researcher with decades of experience in astrophysics, and in 2023 he submitted a paper to the monthly notices of the Royal Astronomical Society that did not try to tweak the Hubble constant by a few percent, or introduce a minor perturbation to the dark energy equation of state. He proposed instead that the universe is approximately 26.7 billion years old, nearly twice the currently accepted value, and that the reason JWST is finding massive, mature galaxies in the early universe is precisely because there was nearly 13 billion additional years of cosmic history that we have been failing to account for. The mechanism Gupta proposed is a fusion of two heterodox ideas. The first is Fritz Zwicky's tired light hypothesis, formulated in 1929 as an alternative to the expanding universe interpretation of cosmological redshift. Zwicky, a Swiss astrophysicist of extraordinary and sometimes contentious intellectual energy, the same man who first proposed the existence of dark matter in galaxy clusters in 1933, suggested that the redshift of distant galaxies did not necessarily indicate recession velocity. Instead, he proposed photons might gradually lose energy as they travel through space, shifting toward the red end of the spectrum through some interaction with the intergalactic medium, in the same way that a ball rolling across a rough surface gradually slows down. The further the photon travels, the more energy it loses, the more redshifted it appears. Distance and redshift would still be correlated, but not because the universe is expanding. The tired light hypothesis has a long and problematic history. It was effectively ruled out by several key observations: the time dilation of supernova light curves, which expands in proportion to redshift in exactly the way expansion predicts, and in the exact opposite way tired light would predict. The thermal spectrum of the CMB, which is a perfect blackbody spectrum consistent only with a hot, dense, expanding early universe, and the surface brightness of galaxies, which dims with distance according to expansion rather than tired light geometry. These are serious quantitative refutations. Gupta knows this. His model does not adopt pure tired light. Instead, he combines a modified form of it, one in which photons lose energy partly through a coupling constant mechanism rather than a scattering mechanism, with a separate idea first proposed by physicist Paul Dirac in 1937, the hypothesis that the fundamental constants of nature are not truly constant, but vary slowly with cosmic time. The coupling constants Gupta invokes are the combinations of fundamental constants that govern the strengths of the electromagnetic, gravitational, and weak nuclear forces. If these constants were different in the early universe, if gravity was slightly stronger, or the fine structure constant slightly different, then the timescales of physical processes in the early universe would be altered, the formation of structures could proceed more rapidly, and the observable properties of high redshift galaxies could be made consistent with a universe much older than 13.8 billion years. In his 2023 MRAS paper, Gupta demonstrated that this combined CCC plus TL model, covarying coupling constants plus a tired light component, could reproduce the angular diameter distances of the CMB, the baryon acoustic oscillation scale, and the properties of high redshift JWST galaxies, while placing the age of the universe at 26.7 billion years. At that age, a galaxy seen at a redshift of 10 has had 5.8 billion years to form, rather than the roughly 500 million years that lambda CDM provides. The mass problems largely dissolve, the maturity problems dissolve. The red monsters are no longer monsters. Now I want to be precise here, because this is where scientific literacy requires a kind of double vision. Gupta's paper was peer-reviewed and published in a reputable journal. The mathematical fits are real. The observation that a universe twice as old would accommodate the JWST anomalies is logically correct. But peer-reviewed publication in a good journal does not mean that a theory is accepted by the field, and the mainstream reaction to Gupta's proposal has been deeply skeptical, not dismissive, but skeptical in the specific way that says these observations need to be reproduced with the correct constraints before we can take this further. The tired light component of the model, in particular, faces the time dilation problem in supernova data that is extremely difficult to circumvent without breaking other well-confirmed observations. And the idea that fundamental physical constants are varying is itself a claim of extraordinary magnitude, because those constants appear in virtually every calculation in physics and chemistry, and their variation would produce detectable signatures in spectroscopy, atomic physics, and stellar evolution that have been searched for exhaustively and not found at the levels Dirac's original proposal would require. This does not make the idea impossible, it makes it highly constrained. And constraint, in the scientific sense, is not a minor obstacle, it is the testing ground on which all ideas must prove themselves. But here is what I think matters about Gupta's proposal, independent of whether its specific mechanism is correct. It represents the serious, quantitative attempt by a professional astrophysicist to confront the JWST anomalies not by adjusting parameters within lambda CDM, but by asking whether the foundational framework of lambda CDM, the interpretation of redshift as purely velocity, the assumption of constant coupling constants, the calculation of the age from H0 directly, might itself require revision. That question, which would have been treated as professionally dangerous to ask 10 years ago, is now being asked in journal papers, conference presentations, and peer-reviewed commentary. The Overton window in cosmology has shifted, and behind that shift is a machine that took 30 years to build and $10 billion to fund. A machine whose story is inseparable from the crisis it is now illuminating, because the people who built it, fought for it, and dedicated their careers to it did not simply build a better Hubble. They built something qualitatively different, a telescope designed specifically to see the epoch that the standard model predicted would be the nursery of cosmic structure, fully expecting to confirm what the models said. What they got was confirmation that the models had been telling an incomplete story all along. John Mather received the Nobel Prize in Physics in 2006 for his work on the Cosmic Background Explorer satellite, COBE, which made the first precise measurements of the CMB and provided the observational foundation for modern cosmological parameter estimation. He then spent the next 15 years as senior project scientist for the James Webb Space Telescope, shepherding it through budget crises, redesigns, delays, political challenges, and the slow, grinding technical work of building the most complex scientific instrument ever placed in space. He was 75 years old when JWST opened its eye in 2022. He had given the telescope half his professional life, when the first deep field images came back, when the light from galaxies 13 billion years in the past fell, for the first time, onto sensors sharp enough to resolve their structures and spectrographs, sensitive enough to read their chemistry. Mather stood in front of an audience at the University of New Mexico and said, "We didn't expect to find what we're finding. That is not a criticism. That is the sound of science working exactly as it should. An instrument is built to test predictions. The instrument makes observations. The observations contradict the predictions. The predictions are revised. This is how knowledge advances, not by confirming what we already knew, but by being startled into accuracy, by the universe's refusal to cooperate with our models." What Mather could not have known, as he watched those first images come down from 1.5 million kilometers away, was that his instrument had not merely resolved a few academic discrepancies. It had opened a window onto a set of problems that, taken together, might demand not a refinement of lambda CDM, but something genuinely new, something whose outlines are still only partially visible, whose mathematical form has not yet been written, and whose implications, when they are finally understood, will reach all the way back to the number on which everything rests, 13.8 billion years, a number built with extraordinary precision by extraordinary scientists on what turned out to be an incomplete foundation. The question now is not whether the foundation needs work. It demonstrably does. The question is what kind of work, and how deep the excavation will have to go. There is a further complication, a complication so large and so recently sharpened that it deserves its own chapter, and, were the world paying close enough attention, perhaps its own front page. Dark energy is the name we have given to the cause of the universe's accelerating expansion. It was discovered in 1998 by two independent teams, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory, the other by Brian Schmidt and Adam Rias at Harvard and the Australian National University, who were both measuring the distances to Type Ia supernovae at high redshift with the expectation of measuring how much the universe's expansion was slowing down due to gravity. Both teams found instead that the expansion was speeding up. Distant supernovae were fainter than expected, further away than they should have been in a matter-dominated, decelerating universe. Something was pushing the expansion outward against the pull of gravity, with an energy density that has come to dominate the universe's total energy budget. In lambda CDM, dark energy is represented by the cosmological constant, lambda, the term Einstein introduced into his field equations in 1917 in an attempt to create a static universe, and later called his greatest blunder. The cosmological constant represents a fixed unchanging energy density of empty space, a vacuum energy that is the same everywhere, at all times throughout cosmic history. Its equation of state parameter, W, is defined as the ratio of its pressure to its energy density, and for the cosmological constant, W1 exactly, not approximately, not on average, exactly to arbitrarily high precision. This value of W-1 is the assumption embedded in every lambda CDM calculation. It is the assumption from which the age of the universe is derived. It is the assumption that determines how the expansion rate has evolved across time, and therefore what the universe looked like at any given epoch in the past. In March 2024, the Dark Energy Spectroscopic Instrument, DESI, released its first major results from a survey of approximately 6 million galaxies and quasars, measuring their positions across cosmic time through the technique of baryon acoustic oscillations. BOs are the fossil imprints of the same sound waves that created the pattern in the CMB. A characteristic scale of approximately 147 megaparsecs that shows up as a preferred separation between galaxies and can be used as a standard ruler to measure how the universe's expansion rate has changed with time. DESI's first data release provided the most precise BAO measurements ever made, and the combination of those BAO measurements with CMB data and Type Ia supernovae data produced a result that sent a ripple through the field. When the data were fitted to a model allowing the dark energy equation of state parameter to vary with time, parameterized as W0 plus WFA1A, where A is the cosmic scale factor, the best fit values deviated from the cosmological constant prediction of W0-1 at a statistical significance of 2.5 sigma, suggestive, not definitive. Then, in March 2025, DESI released its second data release, DR2, encompassing more than 14 million galaxies and quasars. The significance of the deviation from W1 strengthened. The combined analysis, incorporating Type Ia supernovae from multiple catalogues and the Planck CMB data, now shows a preference for W0 slightly greater than -1, meaning dark energy is weaker than the cosmological constant in the present epoch, combined with WC significantly less than 0, meaning dark energy was stronger in the past and has been weakening. The combined statistical preference for this evolving dark energy scenario sits at approximately 3 to 4 sigma across different supernova datasets, still short of the 5 sigma discovery threshold, but strengthening with each new dataset rather than weakening. What does evolving dark energy mean for the age of the universe? A great deal. If dark energy is not a cosmological constant, if it is a dynamical field, varying with time, stronger in the past and weaker now, then the entire expansion history of the universe is different from what lambda CDM assumes. The calculated age from today's H0 value depends on an integral over the entire expansion history. Change the dark energy model, and the integral changes. The age changes. By how much depends on the specific form of the evolution. But the direction, with dark energy stronger in the past, would tend to push the age upward. A universe whose early expansion was more strongly accelerated by dark energy, and whose late expansion has been gently coasting as that energy wanes, might be older than 8 billion years even without invoking new physics at the level Gupta proposes. The DESI result is not yet definitive. The 3 to 4 sigma preference for evolving dark energy could still resolve into a systematic error in the supernova data, the choice of which Type Ia supernova sample to include significantly affects the significance level, a fact the DESI team is entirely transparent about. But the key point is that 3 separate independent lines of evidence, the JWST early galaxies, the Hubble tension and the DESI dark energy measurement, are all pointing from different directions and using entirely different methodologies toward the same general conclusion. The lambda CDM model, with its lambda as cosmological constant and its 13.8 billion year age, is under simultaneous pressure from multiple observational quarters. The probability that all 3 anomalies are measurement artifacts that will evaporate on further scrutiny decreases with every new dataset. The stakes of getting this right are not merely academic. They are existential at the level of cosmological understanding, because embedded in that 13.8 billion year number and in the lambda CDM model from which it is derived, is our entire account of where everything came from, where the hydrogen in the oceans came from, where the carbon in every living cell came from, where the iron at the Earth's core came from, where the photons of light that are, at this very moment, entering your eyes came from. If the model is wrong, not just in its fine details but in its foundations, then our account of our own origins is incomplete in ways we cannot yet fully map. I find that simultaneously humbling and electrifying. The possibility that the story of the universe's beginning may need to be substantially rewritten. In the light of data collected by a machine built by human hands and launched on a rocket from a jungle-edge spaceport on Christmas morning, is one of the most remarkable situations I can imagine a civilization finding itself in. And we are in it, right now, in real time. Before we go further, I want to do something that is not always done in discussions of these anomalies, in popular science writing, in YouTube videos, in social media threads, and that is to apply the brakes, not to the sense of excitement, which is warranted and real, but to the most extreme interpretations which are not yet warranted and which risk confusing the genuine and consequential crisis in cosmology with the much larger and much less justified claim that everything we know is wrong. The lambda CDM model is not broken. Let me be precise about that. It is under pressure. There is a difference. A model that is broken would fail to explain most of the data it is asked to describe. Lambda CDM explains an enormous range of observations with extraordinary precision. The temperature power spectrum of the CMB to parts per million, the baryon acoustic oscillation scale, as measured by galaxy surveys going back to the 2DF and SDSS surveys of the 1990s and 2000s, the abundances of hydrogen and helium produced in Big Bang nucleosynthesis, the large-scale distribution of galaxies, the ages of the oldest globular clusters in the Milky Way, the properties of thousands of observed gravitational lenses. These are not minor agreements. These are detailed, quantitative, multi-parameter agreements that any alternative model must match to be taken seriously, and no currently proposed alternative comes close to matching them all. The crisis in cosmology is not that lambda CDM fails. It is that lambda CDM succeeds at almost everything and then produces these specific, reproducible, increasingly hard-to-explain failures. The Hubble tension at 5 sigma, the early massive galaxies that form too fast, the large-scale structures that are too large, and now the possible evolution of dark energy. These failures are located at the edges of the model's predictions, not at its core. That is why they are serious. Edges are where new physics hides, but it is also why they do not license the conclusion that the Big Bang did not happen, or that the universe is 6,000 years old, or that everything cosmologists have told us is a fabrication. Let me address each anomaly carefully. The early massive galaxies from JWST are real. The spectroscopic confirmations are solid, but a significant fraction of the most extreme initial estimates have been revised downward as spectroscopic data replaced photometric estimates. The most troubling objects remain troubling, but the crisis in this area is best described as the need to revise our models of galaxy formation efficiency, and perhaps the star formation rate density in the first billion years, not necessarily the fundamental age of the universe. Several theoretical modifications to lambda CDM, enhanced star formation efficiency at high redshift, a different halo mass function, or the contribution of black hole accretion to apparent stellar masses can reduce the discrepancy from dramatic to merely provocative. The NASA JWST science team itself published an analysis in 2024 acknowledging that some early JWST galaxies are less massive than initially appeared, specifically because active galactic nuclei were contributing luminosity that had been misattributed to stellar populations. The problem is real and remains to be fully resolved, but it is not yet a clean, unambiguous refutation of the timeline. The Hubble tension is the most serious of the anomalies because it is the most statistically robust and the most resistant to instrumental explanation. The SEIS team has now performed Cepheid measurements using JWST specifically to check for crowding errors in the Hubble Space Telescope measurements that Adam Rias's team had been using for a decade. JWST's superior resolution effectively rules out crowding as the source of the discrepancy. The Cepheid distances, as measured by the superior resolution of JWST, are consistent with the Hubble measurements. The tension between the local measurement at 73 km SAN and the CMB inferred value at 67.4 km SAN persists after the most likely instrumental explanation has been eliminated. Wendy Friedman's TRGB and JEG-B measurements, as I mentioned earlier, come in between these two values at approximately 69.8 km second p. The source of disagreement between Friedman's Cepheid calibration and Rias's Cepheid calibration using the same JWST data is now an active research frontier. There are genuine, honest disagreements among world-leading distance measurement teams about how to properly model Cepheid metallicity corrections and anchor calibrations, and these disagreements carry real statistical weight. But even Friedman's middle value of 69.8 is inconsistent with the Planck value of 67.4 at more than 3 sigma. A moderate tension remains in every scenario, and the question, is it new physics or an undiscovered systematic, remains genuinely open. What is abundantly clear, given the 5 years of JWST science operations that have now accumulated, is that the James Webb Telescope has not simply confirmed an old universe with better resolution. It has delivered a set of observations that require the field to work harder, to refine models, challenge assumptions, and in some cases begin drafting genuinely new theoretical frameworks. The question now being asked in the pages of Physical Review D, in the Astrophysical Journal, and in conversations between cosmologists who have spent their careers in this field, is no longer simply whether lambda CDM is correct. It is what comes after it, what the revised or extended or replaced framework looks like, and whether the data we have accumulated are sufficient yet to distinguish between the candidates. The lithium problem, a long-standing anomaly in Big Bang nucleosynthesis. The observed abundance of lithium-7 in old metal-poor stars is approximately 3 times lower than the value predicted by standard BBN theory, has been hanging around the edges of cosmology for 2 decades without generating a revolution. Perhaps it is a nuclear physics uncertainty. Perhaps it is destroyed by mixing in stellar interiors. Perhaps it is a signal of new physics in the first 3 minutes. That it has persisted without resolution for 20 years, without collapsing the standard model, illustrates the point. Anomalies can survive for a very long time without necessarily indicating that a paradigm is broken. But the simultaneous convergence of multiple strong anomalies, the Hubble tension strengthening as instrumentation improves, the early galaxy problem persisting despite downward mass revisions, the large-scale structure violations accumulating, and now the DESI dark energy signal is qualitatively different from a single isolated puzzle. The standard response to the lithium problem is that it is one anomaly whose cause is likely astrophysical rather than cosmological. The standard response to the accumulated 2020s anomalies is increasingly, among sober and careful researchers, that the model needs amendment, not demolition. Amendment. And what are the candidate amendments? Early dark energy is the most widely discussed, a theoretical framework in which there was an additional component of energy density operating in the early universe, around the epoch of recombination, that briefly contributed to the expansion rate before decaying away, in a manner that would push the CMB inferred H0 upward toward the local measurement and reconcile the Hubble tension without changing anything observable in the late universe. Early dark energy models have been extensively developed and constrained by the Planck data, and while they can reduce the tension, they do not eliminate it, and they introduce new problems. Specifically, they tend to amplify the sigma-8 tension, a discrepancy between the predicted and observed amplitude of matter density fluctuations that is a separate but related problem in the standard model. The resolution of one tension by early dark energy tends to worsen another. This is the characteristic signature of a framework being stretched in multiple directions simultaneously, and each stretch revealing the places where it is thin. Interacting dark energy, in which dark energy couples non-minimally to dark matter, allowing an energy transfer between the two dark sectors that modifies the expansion history. This is another class of models under active investigation, motivated in part by the DESI results, modified gravity theories in which the behaviour of gravity on large scales departs from general relativity in ways that alter structure formation and the expansion history simultaneously, are a broader class still. None of these have achieved the status of a compelling preferred solution. All of them fit some part of the data better than lambda CDM, while fitting other parts worse. The field is, in the technical language, not yet data-driven to a unique new model. It is data excluded from pure lambda CDM, but not yet data selected toward a replacement. This is an honest description of a field in genuine transition. Not revolution, not crisis in the sense of collapse. Transition in the sense that the path forward is not yet clearly marked, and the working scientists navigating it are doing so with impressive rigour and appropriate uncertainty, which is exactly as it should be. Now let us go further, because there is one more layer to this story that most popular accounts do not reach, and it is the layer that I think makes the entire situation most resonant. What does it mean for us, as beings who inhabit this universe, and have only just begun to measure it, if the number we put on its age is wrong? What does it cost us as a civilization if the story we have been telling ourselves about our cosmic origins has a chapter missing? In 2025, cosmology finds itself in the most productive form of discomfort science knows, the kind where the data is unambiguous and the theory is insufficient. This is not confusion, it is not failure, it is what science looks like from the inside when it is on the verge of a genuine advance. The instruments that will carry the field through this transition are already built, already launching, or already operating. Understanding where the evidence is pointing requires understanding what those instruments are designed to do and what questions they are positioned to answer. The Euclid Space Telescope, launched by the European Space Agency in July 2023 and conducting its wide-field survey of the sky from the same L2 Lagrange point as JWST, is designed specifically to map the geometry and growth of the large-scale structure of the universe across 10 billion years of cosmic history. Its primary science goals are to constrain dark energy and test whether the cosmological constant is truly constant, exactly the question that the DESI results have made most urgent. By mapping the shapes of approximately 2 billion galaxies through weak gravitational lensing and their three-dimensional distribution through galaxy clustering and baryon acoustic oscillations, Euclid will provide constraints on the dark energy equation of state parameter at a precision that will either confirm the DESI hints of evolution or push them back below statistical significance. By 2027, Euclid's first major survey results will be available, and the dark energy question will be substantially sharper than it is today. The Nancy Grace Roman Space Telescope, NASA's flagship wide-field infrared survey telescope, scheduled for launch in 2027, is, among other things, designed to perform a supernova survey of unprecedented scale, measuring tens of thousands of Type Ia supernovae across cosmic time, with the kind of statistical power that will resolve the current disagreements between different supernova datasets that currently cloud the DESI dark energy interpretation. Roman will also perform a weak lensing survey comparable to Euclid's, providing a second independent check. The convergence or divergence of Euclid and Roman results will determine whether the apparent dark energy evolution is real or instrumental. On the ground, the Vera Rubin Observatory at Cerro Pachon in Chile, the largest optical telescope ever constructed for survey astronomy, with an 4-meter mirror and a camera capable of imaging the entire accessible sky every 3 nights, began science operations in 2025. Its legacy survey of space and time, LSST, will over 10 years catalogue approximately 20 billion galaxies, track hundreds of thousands of transients including supernovae, and provide the largest photometric dataset in the history of astronomy. The Rubin data will be critical to the sigma-8 tension, the discrepancy between predicted and measured matter clustering, which is one of the tensions currently entangled with the early dark energy hypothesis, and JWST itself will continue operating for at least a decade. Its consumables, the hydrazine fuel used for station keeping and orbit correction, preserved by the extraordinary precision of the Ariane 5 launch that placed it almost exactly on its intended trajectory, requiring far less correction fuel than the conservative pre-launch estimate had budgeted. Each additional year of JWST operations adds depth and statistical power to the early universe galaxy survey and the spectroscopic confirmation of increasingly distant and increasingly anomalous objects will continue to sharpen the constraints on whatever new physics is needed to explain them. What are the most likely scenarios for how this resolves? I want to offer three, in increasing order of how much they would change our understanding of the universe. The first scenario, the minimal revision, is that the Hubble tension resolves to approximately 3 sigma through a combination of improved Cepheid calibrations, improved TRGB calibrations, and a recognition that both the Sayce and Friedman methods carry previously uncharacterized systematic uncertainties that inflate their apparent agreement. In this scenario, H0 settles somewhere between 70 and 71 seconds p. The age of the universe is revised slightly upward to approximately 13.4 billion years, or marginally downward to 13.6 billion years, depending on the specific H0 and dark energy parameters, and the early galaxy anomalies are resolved by modest modifications to star formation efficiency models, and a better accounting of AGN contributions to high redshift photometry. The cosmological principle holds the large-scale structures are statistical outliers, and lambda CDM with minor parameter adjustments survives as the standard model. This is the least dramatic outcome, but it remains a non-trivial revision, and the field's honest assessment is that it requires the systematic errors to be found. They have been searched for, they have not yet been found. The second scenario, modest new physics, is that the Hubble tension requires a genuine addition to the model, early dark energy, or a new relativistic species, or a modified recombination history, or some combination of these. The dark energy turns out to be genuinely evolving, consistent with the DESI DR2 result at 4 sigma, and strengthened by Euclid and Roman data to definitive status. The cosmological principle holds on the very largest scales, but the large-scale structures indicate that the transition to homogeneity occurs at a slightly larger scale than previously assumed, requiring a small adjustment to the inflationary spectrum. The early galaxies are explained by a combination of enhanced early star formation and revised AGN modelling. The age of the universe is revised, perhaps to 14 to 15 billion years, or perhaps down to 12.5 to 13 billion years, depending on the direction the new dark energy physics pushes the expansion history. This scenario requires new physics, but does not require abandoning the Big Bang framework, or the CMB interpretation, or the nucleosynthesis history. It is a revision of the model's later chapters, rather than its opening pages. The third scenario, deep revision, is the one that wakes cosmologists up at 3 in the morning. In this scenario, the anomalies are not independent edge effects, but symptoms of a shared foundational problem. The cosmological principle is only approximately valid at the largest observed scales, generating a systematic bias in the CMB-inferred cosmological parameters that has been present in every Planck analysis. The dark energy evolves in ways inconsistent with any simple scalar field. The early galaxies represent not merely faster structure formation, but genuinely different physics at the high redshift frontier. Physics whose nature is not yet specified, but whose reality is forced by the data. In this scenario, the age of 13.8 billion years is revised substantially, upward or downward depending on the new model, and the revision carries with it a new account of the universe's early history. Rajendra Gupta's 26. 7 billion years remains on the fringe of this scenario rather than at its centre, but the fringe is wider and less clearly fringed than it was 5 years ago. I do not believe the third scenario is the most likely outcome. I think the second scenario is where the evidence is currently pointing, and the evidence will sharpen over the next 5 years into either a clear confirmation or a clear refutation of the specific new physics proposals now on the table. But I hold this belief loosely. Science's record on bold predictions about its own imminent discoveries is not reassuring. What I do believe, with considerable confidence, is that the universe's age will not remain exactly 13.8 billion years, not because the measurements that produced that number were wrong in any simple sense, but because those measurements were made in the context of a model that is now demonstrably incomplete. And when the model is revised, the number will move. How far and in which direction, and what the consequences of that movement are for our understanding of cosmic history. These are the questions that are being actively, rigorously, and brilliantly pursued right now by a generation of scientists working with the finest instruments our civilization has ever built. There is something profound in the fact that a species that has existed for perhaps 300 Zeussan years on a planet that formed 4.5 billion years ago, orbiting a star in a galaxy that began forming 12 billion years ago, in a universe that has been expanding for longer than any of those numbers, has managed to measure its own beginning to within a few % of the correct answer, using nothing more than mathematics, light, and the human willingness to keep looking upward and asking why. That we are now discovering that the answer is slightly different from what we thought. That the margin of our incompleteness is itself a discovery of enormous significance, is not an embarrassment to science. It is science doing precisely what it promises to do. It promises not to have all the answers. It promises to narrow the error bars, slowly, painfully, with controversy and revision, and the occasional humiliation of a discarded certainty. It narrows the error bars. And right now, in 2025 and beyond, those error bars are being narrowed faster than at any previous moment in the history of cosmology. What they will converge on, what number they will eventually stabilize around, what new and stranger story of the universe's beginning they will eventually force us to tell our children, that is the frontier. We are the generation that found the gap. The generation that builds the bridge across it is already being born. There is a peculiar intimacy to the number 13.8 billion years. You can write it on a post-it note, you can say it in a single breath, and yet it is an attempt by a short-lived species of pattern-recognizing primates, who spend most of their lives worrying about things that will be forgotten in 100 years, to measure the total duration of everything that has ever existed. There is something almost endearingly ambitious about the whole project. Almost because the ambition is not merely emotional, it is operationally necessary. If you do not know how old the universe is, you do not know how much time there was for hydrogen to collapse into the first stars, for those stars to forge and scatter the heavier elements, for those elements to accumulate on rocky planets orbiting second-generation stars, for chemistry to achieve the extraordinary improbability of self-replication, for self-replication to achieve the further improbability of nervous systems, and for nervous systems to achieve the final improbability of wondering about all of this. Every link in that chain has a timescale, and the total time available determines whether the chain is plausible or not. The age of the universe is, in a deep sense, the age of the possibility of us. So when JWST sends back an image of a galaxy burning at redshift 44, a galaxy that existed when the universe was less than 300 million years old, already assembled, already forming stars, already producing oxygen through the violent deaths of its earliest stars. The disruption is not merely scientific, it is ontological. It is a revision to the story of how we got here. What I keep returning to, and I have read and reread these papers over months of preparation for this script, is the specific quality of uncertainty that the current moment in cosmology carries. It is not the uncertainty of ignorance. We know an enormous amount. The Big Bang happened. The universe expanded from a state of extreme heat and density approximately 8 billion years ago, give or take some number of billions that is currently contested. The CMB is real, its physics is sound, its measurement is among the most precise in the history of science. Dark matter exists, even though we do not know what it is. Dark energy exists. Even though we do not know what it is or whether it is constant, the large-scale structure of the universe is determined by the tiny quantum fluctuations in the first fraction of a second of cosmic time, amplified by billions of years of gravitational growth into the web of filaments and voids, that JWST now resolves with the clarity of a geological survey. None of this is in doubt. What is in doubt is the specific quantitative values, the Hubble constant, the dark energy equation of state, the formation timescales of the first galaxies, the upper limit on the scale of cosmic homogeneity. And those values matter enormously, because cosmology is not a qualitative science. It is a science of numbers, and numbers carry the difference between a model that is fundamentally correct and a model that is fundamentally incomplete. The three unanswered questions that I opened with at the beginning of this story are still unanswered. How old is the universe? If JWST's galaxies demand more time than 13.8 billion years provides, and if the Hubble tension demands a different expansion history than lambda CDM assumes, and if dark energy is evolving rather than constant, then the answer is genuinely unknown to within perhaps 2 or 3 billion years in either direction. That is an enormous range of uncertainty for the most fundamental measurement in cosmology. What is dark energy, really? DESI's Dia-2 results, Euclid's first data, Roman's planned supernova survey, and the accumulated depth of JWST galaxy surveys will sharpen this question within this decade. But the answer, the mechanism, the physical nature of the field or fields responsible for the accelerating expansion, is not yet in sight. And is the cosmological principle the complete truth, or only a useful approximation? Alexia Lopez's giant arc and big ring sit in the sky at a cosmic distance of 9.2 billion light-years, and a diameter of 1.3 billion light-years, waiting for an explanation that does not yet exist. Whatever that explanation turns out to be, a statistical fluctuation, a new type of large-scale structure, a violation of isotropy, or something currently unnamed. It will tell us something important about the universe's deepest geometry. These questions are not rhetorical placeholders. They are the active research frontiers of the most observationally productive period in the history of cosmology. The instruments are running. The data is accumulating. The theorists are working. The answer, some version of it, sharper and more complete than anything we have now, is coming. And when it arrives, it will not end the story. It never does. Science doesn't give us destinations. It gives us better questions. Questions with more precise coordinates. Questions with sharper edges. Questions that fit our current ignorance more accurately than the vague, enormous questions we had before. The universe will not explain itself on demand. It offers its secrets slowly, at the speed of photons crossing 13 billion years of void, arriving one by one into the golden mirrors of a telescope that someone spent 30 years building in the desperate and justified hope that the cosmos would surprise them. It surprised them. It surprised all of us. And somewhere out there in the infrared dark, the oldest light of the universe is still travelling, still arriving, still carrying, encoded in its stretched and ancient wavelengths, the answer to a question we have not yet learned to ask. We are the generation that found out the number was wrong. The generation that finds the right number belongs to whoever looks next.